Welcome everybody. Thank you for joining today's webinar, Proactive Condition-Based Maintenance Strategies for Improved Plant Reliability, co-hosted by ISA and FDT Group. My name is Michaela Cooper and I'm with ISA and I will be hosting today's webinar. Before we get started, I would like for our presenter Ian to tell us a little bit about himself. Ian?
Well, thank you, Michaela. And as you can see, I'm an ISA certified automation professional, and I've been involved in industrial networking and communications for approximately 20 years now. I've also had the honor of being the chair of the ISA 103 Standards Committee, which is the organization that brings the international IEC standard to ANSI and hence into the United States. And so I'm fortunate as well that we have my co-presenter today, Gabor, will be sharing with us how he, or how more accurately they, at the MOL Danube Refinery were able to make effective use of FDT technologies. So what we'll be talking about today are some of the challenges that we face in today's industrial environment. How, by changing the way we take advantage or use the intelligent assets, in particular our field devices, can provide significant bottom line benefits, and how, migrating from the check engine light, which is effectively a common trouble alarm, to more in-depth analysis can, with these tools such as FDT, that so we can see in depth what the cause is. And then Gabor will come and give some examples of how he took advantage of his smart or intelligent check engine light to improve the reliability and bottom line profits of the MOL Danube Refinery. And I'll come back, give wrap up, and we'll answer any questions that may arise. So if we look at today's manufacturing environment, the big things that are driving all of us is we need to improve plant reliability, and one of the key ways to do that is to move from reactive or predictive condition-based maintenance strategy to a proactive, so working on the right product at the right time. And so what that would enable is an overall lower cost, and therefore allowing us to not only do more with less, but likely put more production, more product through our facility with minimal capital investment. So I'm sure that we've heard this: more with less, be more efficient, increase productivities tune in various different ways, and so it's a pretty familiar song to all of us. But how do we do that? And so the challenge then becomes, what can we do to improve plant reliability? And the lowest cost, the simplest thing, is to make better use or maximize the use of the intelligent assets we already have on site. And so that's the net result is increased competitiveness, increased reliability through lower operating costs, and of course, whenever you take a dollar out of the operating expense, that goes straight into the profit line and makes your management team very happy. So how do we look at instruments today? So most of us just look at our transmitter. So in this case, we have an example of a level transmitter up at the top, and all we really do is, what's the PV? What's the 4 to 20 milliamp? What's the output of the device? However, the real smarts are inside the device. So let's have, if we tunnel down inside and take advantage to what are all those little microprocessors doing inside. So if we take a look at the inside of our level transmitter, here's an example of, or just some of the stuff that you would get by doing so. So this window here in the frame is the navigation bar, so you can see all the devices that are connected onto our intelligent I/O card. Then on the right, we have now a graphical picture to tell us what the span of our radar gauge is, and as you can see, again, another navigation bar here in the orange or yellow to tell us, again, how to navigate from, the various maintenance activities or configuration activities that we might be performing. Then on the bottom, we can actually see the actual reading shown as a graphic. And I don't know about you, but I'm certainly able to see things or put things in context a lot more easily when I see it graphically rather than as an example, a big table or a series of numbers. So that's an example for our level transmitter. Here's the similar for a valve. Obviously, valves are a critical part of any process. Certainly, one of the bigger expenses or big spend components. So if we look at our valve here, in this case we're looking at some Foxboro. On the lower right, we have we have a navigation pane, and now we're looking at the valve signature. And one of the great things about the capability of this valve signature is because we have the richness of effectively almost like a programming environment, we can automate a lot of these procedures so that we say, okay, signature test, and away safely turns the device into an offline mode, runs the test, and then brings the device back to operational mode. The second graphic, again, you can see we've just navigated on the navigation bar on the left. We've just selected another option. Now we're looking at position histograms. So this is basically telling us how much time our control valve was operating in the different bands from 0% up to 100%. And as you can see, this valve is properly sized because we're spending the vast majority of our time in the 60 to 70% band. So the valve is almost always in that 60 to 70% open range, which is where we want to operate, is typically in the 25 to 30, say up to a maximum of 80% open. So very quickly, a snapshot, and I can see how my asset, in this case a valve, is operating. Now, to access that information, we have a number of different ways. You can use a point-to-point solution, and that's typically what you would be doing if you were doing commissioning or perhaps maintenance. Obviously, there are some maintenance activities where you have to be directly connected to a device, or if you're just doing some diagnostics. So if you're not wanting to invest or build the complete infrastructure, you can get started simply by using, as we've demonstrated in the top, a USB modem, or in the bottom, most handheld devices also have the ability to support DTMs and communicate with your device. However, the real benefit of going with an integrated solution is we can transparently route a message across a wide range of networks and protocols. And so now we can integrate all this data into a server or a database, thus making it possible for us to track trends. And in some cases, we can even make some of the changes to our devices without leaving the comfort of our office. Certainly kind of important here in January in Canada, and probably for all of you down on the Gulf Coast now that we're getting here to summer. So let's just see how that might work. So down here in the bottom, we might have a heart device. It then goes into a gateway where we're converting it, for example, to Profibus DP. Then the Profibus DP network connects to Profinet, and from Profinet, we are then accessing the network with our HMI operator stations, maintenance stations, or engineering workstation to read the smart information down at the bottom, shall we say, of our protocol stack. And speaking of protocols, FDT supports these protocols that you see here. So you might have in your facility, you might have Ethernet IP to connect to some of your PLCs. Then those PLCs might use HART to talk to the devices themselves, or you may have motors that are coming in on DeviceNet, or pretty much everywhere you have some form of Modbus. And so now you can link or communicate through all these protocols with one single interface, and therefore gain access to all of your intelligent information from one place. So looking again at another example of where we might use an FDT, we have here a partial stroke test, and obviously it's critical to do partial stroke testing on safety systems. And so we can not only see the results, but also store and archive comparing historical results as well. So that brings you to the question of, our check engine light. So yeah, it's good if we're getting in there and looking at things at the right time, but that's not always what happens. And so then we have the check engine light, or as I call it, a common trouble alarm to monitor all this information. So when you see this light in your car, does that mean, is it going to unexpectedly shut down and leave you stranded on a freeway? That light doesn't really tell you the condition or seriousness, but we certainly all pay attention to it. So typically what you do is you need the tool to analyze what is the cause, right? So what's continually happening in our car is the computer is checking all the sensors, it detects a problem, turns on that common trouble alarm, and if your neighbor is mechanically inclined, you could speak to them and they don't have the right diagnostic tool to go and read the actual cause of that problem or read the sensor information. They say, well, it might be this, it could be that. However, with the correct diagnostic tool, your mechanic is able to go in and determine that, with today's engines, when you took your gas cap in gas the last time you fueled up, instead of giving it 2 clicks, your gas cap only had 1 click, so you don't have the right amount of, shall we say, back pressure on your gas can, on your fuel tank. And so, just by using the diagnostic tool, you're able to quickly, resolve down right to the source of your problem. However, the common trouble light is kind of just that. It's just too generic. So a German end-user organization called NAMUR decided that what we really need are 4 trouble lights to help tell us at least how much we should worry. And so the first row is maintenance required, and what really that means is you have to go look at this as soon as you can. The next one is out of specification, which means that, hey, you told me that I should expect to operate in this range or under these types of conditions, but I'm still working or functioning, but I'm now outside those limits. So a real simple way would be, you told me that my calibration range is 0 to 100. I'm now reading 105. What should I do? The one you don't want to see, of course, the notorious, the one that causes fear, is failure, which means the device has failed. The good thing is at least you can see that something has gone wrong. And then the last one here is check function, which means that someone is actually working on the device and trying to correct or remedy something that has been identified, for example, that some maintenance needs to be worked. We also have in the bottom box two symbols to tell you whether the diagnostics are actually engaged or turned on or passive. So we have the green box and the gray box to do that. So with that bit of a background of just what is possible with the FDT technology, then we have another example here. Again, this time we're using a foundation field bus device, and you can see we've got the 4 categories, and here you see that we have a mismatch on the function block, which is causing a failure of the device to effectively communicate with the host. But look at the granularity that you can obtain through the intelligence of your device. So you can see if it's out of specification because of, as I indicated, out of the operating limit, or there's a process alarm or some similar alarm. So right away, when you're going to troubleshoot that problem, you know what to expect when you go out to look at the problem. Similarly, Foxboro have with their positioners. So we can see that on the top, everything's green, so the positioner is functioning properly. In the bottom, someone is doing some maintenance on the device, the blue triangle, and that's what the components that are being affected are also shown in blue. And now we're over to Gabor, and he will give us some examples of how they've taken advantage of the intelligence in their devices to drive asset management and reliability at their facility.
Hello everybody, my name is Gábor Bereznai from Hungary, from MOL. My presentation is about reliability-driven asset management using hard communication. First, let us see the operation area of MOL Refining. What distinguishes us from a multinational corporation like Shell? In a nutshell, our achievements in areas of high mechanical availability and pretty low maintenance cost indicators based on Solomon's study. The other key factors is our process safety performance. Our safety performance last year was free of any accident. How did we achieve all this? One of the key factors was our organization's innovative spirit. What do I mean by that? We changed over from corrective approach to preventive and predictive maintenance and implemented online condition monitoring system for rotating, static equipment and instrumentation and process control. More small in the world, but strong in the region. Here you can see this map about our sales directions, and the product slate covers from the fuels to the chemical products. MOL has 4 refineries and 2 petrochemical sites. I come from the Danube Refinery, which is the flagship refinery of MOL Group. The period of 2004 to 2008 was the golden age of European oil refineries. Stable demand for oil products and the deficit in conversion capacities made the oil refineries highly profitable. But after the global financial crisis of 2008, situation in the European oil refining industry changed significantly. Decrease in demand for oil products that hit Europe in 2009 led to reduction in throughput of European oil refineries. This picture shows the European refineries in order of profitability. Danube was the 4th most profitable company in 2008. But after 2009, the downstream margins are melted as icebergs. That time, the pay setters took around 4 to 6 USD on a barrel compared to 2008. Now some oil companies produce loss, especially small and less complex refineries. Since 2009, producers have shut down a number of oil refineries in the Atlantic Basin region. However, this seems to be insufficient as many European oil refineries have low profitability, while their utilization remains rather low. Quite a few low-efficiency oil refineries continue to function. Oil companies are unable to radically cut operations due to the pressure from local authorities and labor unions. High risk of shutdown is especially certain for small oil refineries with low level of complexity, because such oil refineries have high per unit operating cost. To solve it, today even engineers should take into account economic aspects while they keep on working with the same technical professionalism as engineers. The question is how they can wear two hats at the same time. With a good housekeeping, due diligence approach, engineers should act as if they owned the assets, paying attention to their technical and business viewpoints at the same time. So if we want to set the pace and not only to keep it, we must increase our efficiency without ever slowing down. As shown in the graphic, there are two paths to archiving better performance, which Solomon defines as high availability at low maintenance cost, highlighted in gray. Reducing cost alone is not sustainable. Only reliability improvements creates recognizable, sustainable, lower costs. And here is our famous pyramid. The very first step was to develop a book of internal standard and create maintenance and automation development strategy in order to integrate our systems at various levels from the bottom line to the sub-PM. More predictive and proactive actions, less reactive. That was our motto in our availability increasing efforts for economic survival of our division. In this slide, you can see a comparison between units which equip with field instrumentation maintenance system. We call it FIMS. These bars are year by year colored with light blue, and where there are no FIMS at all, highlighted with dark blue. The size of the units are similar, expressed in KEDC, which means kilo equivalent distillation capacity. MOL has executed many reliability improvement actions since 2008, but we reached the biggest benefits where FIMS were introduced. You can see the difference where we use FIMS. There the production losses are smaller due to instrumentation breakdowns, comparing the units where FIMS not introduced. Here is an example where the usage of FIMS had become the part of the daily routine. In this unit, which is the delayed cooker unit, later on the FIMS was connected to the SAP PM. Here the corrective manually entered work orders were replaced by FIMS generated work notifications. These notifications are preventive actions comparing the unit operators entered mostly reactive type work notifications. Since 2010, the number of manually entered work orders are stagnating, that give us a positive feedbacks about the effective usage of the online control valve diagnostic system in this unit. But how is this system works when in use? Let me explain it with an example. Say, one of the control valve gets stuck. In this example, you can control it in opening direction without any problem. But when it comes to closing, it is faltering. Nothing can be seen from outside until the diagnostic system detects stress in the valve. A warning is sent to the FIMS and subsystem, and so it is escalated to the level where the responsible people perform the risk-based work selection. We simply call it RBWS, and take a decision based on the consequence and probability of the occurrence of a failure and on the maintenance strategy. Applied to the given equipment, a decision about notification is serious, which ones can be postponed and which ones do not need any attention at all. Thank God that decision making is very easy, because 95% of all automatic notifications from the system are well grounded and can be readily accepted. Here, using predictive notifications, we can save a huge amount of money avoiding unit outages. Here you can see an example picture, the tool what our experts use under PRM software for control valve diagnostic. On the left side you can find a list of assets. In the middle there is a history viewer with the events. You can see the middle, the object criticality and the message priority. These two important parameters help us to select the most problematic items. And here you can see an example for the device type manager tool. These are very powerful to deeper analyze the selected bad actors. And finally, what lessons we learned? Some people say this is one of the sexy systems that doesn't give us too much benefit. They are, if you fail to understand their usefulness and to exploit the opportunities hidden in them. What benefits we would miss without using this system? Information gained on time to reduce risk of failure, insight into the technical condition of equipment items, for example the control valve diagnostic, prevention of emergency shutdowns, a systemized framework for arranging our daily work routine, utilization of inherent capabilities instead of leaving them idle because they have been there anyway since we paid big monies for the technology. Personal's continuous learning for the sake of the company as well as for own sake. Because preventive information from heart is the same to a maintainer as alarm resulting changes in operating parameters to an operator. Can you imagine a process unit without alarms? It can only operate or shut down without warning. How does it feel, ladies and gentlemen? We didn't like that feeling. And that's why we opted for the flexibility that heart can give us. Put our company among the top performer in terms of safety, environment protection, and even productivity. As for our future plans, a new paradigm will be implemented. We intend to roll out benefits of hard technology to the entire life cycle of our assets, simply because we know the system is capable of following the equipment from cradle to grave. We also want to carry on the integration and make use latest technological development HART can offer us. Thank you very much for your honoring attention. If you have any question, don't hesitate to contact with me.
Well, thanks for that. Thank you very much for that, Gabor. It's very interesting and put into perspective just what is possible with the appropriate use of the intelligence in our devices today. So, what we've learned is that knowing the condition of our intelligent assets facilitates the transition from a predictive to a proactive maintenance strategy, and changing the view from PV only to looking inside the device and using an intelligent check engine symbols allows us to put the plant resources to work where and when they're needed. There are huge savings and improved plant reliability possible if we start using these assets to help us become more intelligent about how and where and when we perform our maintenance. And increased plant availability and reliability will certainly reduce costs, where cost cutting alone is not the answer. It's intelligent use of reducing costs in the right place that really contributes to the bottom line. So if you would, we'd like to thank all of the sponsors for today's event shown here. And as you'll probably recognize, many of these folks are major suppliers and used in your facility. And if you'd like to learn more, please use any of these links here. The ISA standard, or the ANSI standard, is ISA 103. The link is on the upper right. If you'd like to contact myself or learn more about or have any other questions that are not yet answered, please feel free to contact Maggie through the link on the left. And so thank you again for joining us, and we'll pass you back to Michaela.
Yes, thank you both. This concludes the Proactive Condition-Based Maintenance Strategies for Improved Plant Reliability webinar. We thank you all for attending, and we hope you acquired useful information and hope to see you again in one of our future webinars. Thank you.